After the video, I want 3 main takeaways after the video. 3 main takeaways. Wendy, you took some notes. What's a takeaway? Like, what's one thing? Does not have to be earth-changing or earth-shattering. But what's a takeaway from watching the video that you're like, I haven't seen that before, or that's interesting, or I didn't realize that, or I learned something new.
Implicit differentiation relies on the chain rule but looks low.
Yeah. Good. So we talked about that yesterday. We sometimes take some things for granted in math. We operate with y and x so frequently, we don't often stop and think about what they represent. Would you agree with that? Like, y equals something x. We get so conditioned of seeing it that way that we don't really stop and think, okay, x is independent and y depends on x, right? And we say independent variable and dependent, but y depends on x. Y is a function of x, and therefore anytime you see a y, it's not just a single variable. The book uses the letter u, right? Let u be a function of x, or v be a function of x. And so when you see a u or a v, it's not just, u squared. The derivative is not just 2u. Does that make sense? It's 2u to the first. And if u is a function of x, you have to multiply times the derivative of the inside. Du dx, or u prime. Okay? Chain rule. So anytime you see a dependent variable, you have to think chain rule. And so implicit differentiation it's preparing us to think of when you can't solve for y, or even next chapter when we have what are called related rates. I don't want to get too far into this. I just want to get you thinking about it. What if you throw a rock into a pond? We've talked about that before, how the ripple goes out. Doesn't the size of the ripple, or the radius, depend on time, doesn't it? What is the area? Okay, say calculate the area. Take a picture of this ripple from above. Calculate the area of that circular ripple. The area depends on the radius, but the radius depends on time. So if I say a equals pi r squared, and I say take the derivative, a equals pi r squared, and we never write it like this, but isn't it really a of r? Couldn't I write a of r? Area is a function of radius. And if I say take the derivative and tell me how fast is the area changing when the radius is 10 feet? Listen again. Listen very carefully to that. I can't emphasize this enough. How fast is the area changing when the radius is 10 feet? I'm asking a rate. How fast is area changing when r is 10 feet? Area depends on radius. Radius depends on time. So I'll leave it at this. Is r just r? Is it an independent variable? Or in that problem, is r a function? R is a function. R is a function of time. That's kind of weird, isn't it? It's really r of t. So if I say take the derivative of this, it's not just 2 pi r. It's 2 pi r to the first times the derivative of the radius. Not with respect to the radius, with respect to time. That's in chapter 4. So you have to understand, when we're talking about implicit differentiation, you have to understand what is the independent variable. And if it's not the independent variable, then it must be a function, and you have to use the chain rule. Another takeaway, then we'll move on. I guess we'll do 2. Cole, I bet you had a good takeaway.
I thought it was interesting how she described, I think the first example had x squared. How she described it as it was 2x times the derivative of x.
With respect to x?
Yeah.
Mm-hmm. Good. Wasn't her name Verge Cornelius? Wasn't it? Did she introduce herself?
Maybe.
Entertaining. Let's review the worksheet real quick. Did you guys get D&E for number 1? Number 2, right end behavior model. Did you get X? Is a good right end behavior model? X. And did you get e to the negative x was a good left hand behavior model? With work. We're going to fly through this. For number 3, did you get a equals 4 that would make it continuous? That was a little tricky when we first went through that. Are you guys okay with that now? Continuity. The y values have to match up. Plug in x, solve for a. Okay with that? Next one. Determine whether the function has a tangent. Well, to have a tangent, it has to be smooth and continuous. Check for continuity first. Plug in 3 pi over 4. You should have gotten radical 2 over 2 and negative radical 2 over 2. It's not continuous. You can stop there. What would you do if you had to check for smoothness? What if it was continuous? Don?
Check the slopes.
Check the slopes. Good. What's the slope of the top one? Well, the derivative is cosine x. You'd have to plug in 3 pi over 4. The derivative of the bottom one? Negative sine of x. Plug in 3 pi over 4. And if those values were the same slope, then it met and had the same slope coming from the left and right, oh, it's smooth as well. That would be the process for checking. Number 5, you had to use the good old limit definition of a derivative. Limit as h goes to 0. I got negative 2. So you should have gotten the slope of the tangent line is obviously, we have a great benefit here. And they're not going to ask you this on the AP test. They're not going to say, use the limit definition to find the derivative. They're going to disguise it. They're going to disguise it in there. All right. We have the benefit of knowing what the derivative is going to be, right? We have rules for this. It's the power rule. So we know it's going to be negative 4 minus 2x, negative 4 minus 2x. And then if you want to find out when it has a horizontal tangent, you set that equal to 0. X equals negative 2 is when it has a horizontal tangent. So yes, I want to see this process, but you know what the answer is going to be. You can use the shortcut rule to do that. Number 6, displacement was a, negative 4 meters. I wasn't really picky on the quiz about if you included units or not, but I'm going to start being picky. You have to understand units in this class moving forward, because as we apply these things, you need to understand what it represents. So make sure you have units on these. A was negative 4 in meters. B was 0 meters per second. Notice, oh wait, hold on. Letter B. Did I say during the first 4 seconds, or did I change that on your paper? First 4 seconds? So do you agree you could not have used the displacement from part A? Am I speaking a different language? Average velocity is displacement over time, correct? As long as it's over the same interval. A was from 0 to 2. But part B said during the first 4 seconds. So you can't use s of 2 minus s of 0 in the numerator. On the quiz, I did that. I said find the displacement and then find the average velocity, same interval. So you could use that. Okay? Wendy.
Why do you not divide by 2?
On which one?
A.
Displacement is just final position minus initial position. If you divide it by 2, you're finding average velocity. Part C, just the derivative, find the velocity, and you should get 4 meters per second. All right, 7, equation of the normal line. You need the slope of the tangent line. So you have to take the derivative, plug in pi. And then opposite reciprocal. So the tangent slope was negative 1. The normal slope should have been positive 1. And then you need the y value. You had to plug in pi into the original. Get y equals negative 1. So the equation of the normal line is y, 2 ways. Both ways are fine, right here. Either y plus 1 equals x minus pi, or if you solve for y equals x minus pi minus 1. Eight. Looked a lot like a quiz question. I want you guys to practice it again. practice that process again. Make sure you use the product rule. Are we okay now recognizing the overarching derivative rule? Are we still struggling with that? If you're still struggling with that, you want to find resources. There's tons of resources. If you just Google chain rule practice, that's actually the worksheet I gave you guys. And I actually didn't even give you all the problems on the worksheet. Last week when we did the chain rule worksheet, there's problems on there we didn't do. I didn't assign. They're on the back. The answers are on the back. If you want to do some more practice, do some of the ones I didn't assign. Check them on the back. But you have to start recognizing the rules here if you're not yet. Questions on the worksheet? All right. Implicit differentiation. You have your intro. We talked about that. So here's a graphical explanation of when this might happen. This is weird. This is really weird because every derivative we've taken so far, if I say find the slope at a point, there's one slope because there's one point. If it is not a function, do you agree this does not pass the vertical line test? If it's not a function, if it fails the vertical line test, this is kind of weird. If I say find the slope when x is 2, which slope? X equals 2 comma 4, 2 comma 1, 2 comma negative 7, I don't know. There could be 3 different slopes on this graph, couldn't there? That's weird. So you wouldn't need the slope at an x. You need to find the slope at a specific x comma y. Does that make sense? On the worksheet, when I wanted to find the slope, on this graph. All I had to do is plug in an x into the derivative and get the slope. And then how did I find the y? I plugged the x into the original to get the y. There's only one output. If it's a relation, you may have different outputs for the same input. And in this scenario, this is another one of those cases where you cannot solve for y on this graph. All right. So what kind of, I don't want to get too far into this. It's really interesting though. What kind of functions have you seen that are non-functions, that are relations? Well, go for it, Cole. What do you think? Circles. X squared plus y squared equals r squared. Right? Not just positive square root of something, also the negative square root of something. Sideways parabolas. So circles, parabola, sideways parabolas, ellipses, hyperbolas. Some of the conic sections have these. And so there's a ton of connections to optics. We've talked about optics a little bit. If you want to find the normal line to focus that light in the eye onto the lens, you need to find the normal line. You have to be able to find the derivative, and then find the point of tangency, and then find the normal line, and find the point. Okay, a lot of derivatives going on here. A lot of dealing with either a function or if it's an ellipse, a relation. So I will slip up sometimes. When I say let's find the derivative of this function, I may slip up and call it a function because we do it so often. But if it's not passing the vertical line test, technically it's called a relation of x. So our first one, we're going to take the derivative of this implicitly defined function. Now, there's going to be a process. Those of you process people, Mr. Westphal, just tell me the process and I'll follow it. We'll get to that on the next slide. Right now, we're just going to do this example and see it through. My encouragement to you would be if it's given to you like this, don't try to rewrite it. Don't try to solve for y if it's given to you like this. There may be times where we will, if it's really easy, but don't try to solve for y. We're going to take the derivative as is. What's the independent variable? What's the independent variable in this problem? X. How do you know? They tell you find dy dx. Find the derivative of the y function with respect to x. That tells you everything you need to know. So is y just a letter or is y a function? Y is a function or relation, we don't know, of x. So anytime we see a y, chain rule, derivative of a composite function. Y is a function. So you may want to do this. Anytime you see a Y, you may want to put parentheses around it. Not that they're necessary, but just to think, oh, that's a chunk. That's a quantity. It's not just a letter. And so as we take this derivative, we have to think, what's the appropriate rule? And it is the power rule. It's really a power chain rule. 2 times 3 is 6. Leave the inside alone to the first power times the derivative of the inside. What's the derivative of the inside? dy dx. Very good. Plus, next term. Be careful. If it were just y, if it were just a y, not a 2y, if it were just y, what's the derivative of y? dy dx. What's the derivative of 2y? 2 dy dx. It's the constant multiple rule. The constant goes along for the ride. It's 2 dy dx. Not a product rule. You don't have two functions of x being multiplied. Constant multiple. Just like the derivative of 2 sine of x is 2 cosine x. You with me? What's the derivative of 5x with respect to x? 5. And like Cole said, she brought up the point, could you say 5 dx dx? Isn't the derivative of x with respect to x dx dx? But that's just 1. Not worth writing. Well, I want to find dy dx. Don't I want to gather all the dy dx terms on one side if they're not already? Yeah, if we're going to solve for dy dx, I have multiplication, I have addition between. I can factor out a dy dx. What's left inside is 6y plus 2. If I want to find dy dx, my last step to get dy dx by itself is to divide. That is my final answer. Does that make sense? How would I find a slope? This is interesting. Slope depends on what? Someone said it. The y. The only thing you need to know to find a slope on this relation. I don't see any x's in this dy dx. I don't see any x's in this slope function. I just see a y. The slope depends on y. That's weird. So for any y value, it's going to have the same slope along that y value. So what's the process for this? Step 1, you're going to take the derivative of both sides with respect to x. Step 2, you're going to collect all the dy dx terms on one side. Then you're going to factor out dy dx and then solve for dy dx. So if you're a step person, you want to have a 4-step process to solve implicit derivatives, there you go. Take the derivative with respect to x, collect all the terms on one side, factor, and solve. Now, you notice I put in red or y prime. Some people like to write, instead of dy dx, y prime. Be careful. I mean, if you have if you're doing a chain rule and you did 2y to the first and then y prime, I think you could probably see how some people, you could get confused by a first power versus a prime symbol. Yeah, you'd be living dangerously. It might excite somebody. You just have to live for it. Oh, is that a 1 or a y? Is it a prime? Gets your blood pumping. That's sad if that's the case. If that's what gets your blood pumping. All right, so we kind of alluded to the lenses and tangents and applications for this. There you got your light ray. Have you heard the expression, the angle of incidence equals the angle of reflection? Is that a science term you've learned? Now, if you've ever played pool, you've realized that angle of incidence. Okay, so I hit the ball off of this rail or bumper. I don't know what they call it. Rail. The angle of incidence, whatever that angle is, equals the angle of reflection. Whatever angle you hit it off, the wall will come off at the same angle. Okay. Light works the same way. So we got our tangent to the curve, we got our normal line, point of entry, and then the focal point is going to be somewhere on the normal line. If it's not, then you have to adjust it. So as we deal with these, you're going to get some funky equations like that. So let's do a quick little exercise. First term, name that derivative rule. X to the fourth. What? You don't have to tell me what it is, but what's the rule? Power. Very good. Just a traditional power rule or a chain rule? I mean, and if you get confused and you accidentally do the chain rule, 4x cubed times dx 1. Okay, didn't really hurt you. It's okay, as long as you do it correctly. Next term, name that rule. What's the overarching rule? Products. Good. Within the product rule, you're going to first x squared times the derivative of the second. What's the derivative of y squared? Just a power rule or a power chain rule? Power chain rule. Anytime you see a y, you need to be thinking chain rule. And then minus y squared is just a singular, not a product rule, just a singular power chain rule. Let's do this one. And then we're going to have to find the equation of the tangent line and normal lines. It's going to take a little while. Settle in. Get comfy. Let's go. All right. The derivative of x to the fourth is 4x to the third plus. All right. We got a product rule. We got first x squared. Derivative of the second, 2y to the first times dy dx. 2y dy dx. So we got first times the derivative of the second plus the second times the derivative of x squared, which is 2x, minus what's the derivative of y squared? 2y times dy dx. A common mistake, people just put 2 dy dx. That's where if you want to use parentheses, you could say 2y to the first times dy dx. Again, they're not necessary. It's just some people get comfortable by using them. And then what's the derivative of 0? 0. The way I will be doing this all year, you have to have some sort of writing sequence, order of letters and numbers. The way I will always do it, unless I mess up, is numbers first, then x's, then y's, then dy dx's. That way, if you want to combine like terms, you can see the order, you can match up the like terms. So for me, this would be 4x cubed plus 2x squared y dy dx plus 2xy squared minus 2y dy dx equals 0. For you step people, step 1 is to take the derivative. Got it. Done. Step 2, collect all the dy dx terms on one side. Well, this is a dy dx term, and this is a dy dx term. They're going to stay on the left side. Everything else gets moved over to the right side. So we have 2x squared y dy dx. Don't skip steps here. You're just asking for trouble. Minus 2y dy dx. I have to subtract the 4x cubed and subtract the 2xy squared to the other side. Step 3 is to factor out dy dx. That's why we collected them all on one side. Got this all done, Tiny?
Yeah.
Impressive. dy dx. Don't fail me now. Negative 4x cubed minus 2x. That's a y squared, isn't it? My board's glitching out on me. All over 2x squared, squared y minus 2y. That is my derivative. Pretty messy, huh? Guess what we're going to plug in now to get the slope. Let's go. What is it? Radical 2 over 2, comma. We have x's and y's, don't we?
Oh yeah.
We just plug in radical 2 over 2 in for x. Now, you guys are stressing out. Look at you. Some of you are getting hives. Palms are sweaty. Knees weak. My goodness. Radical 2 over 2. Radical 2 over 2. Let's get the slope of the tangent line. Now, a little word of wisdom. Are you ready? X cubed is going to be radical 2 over 2 cubed. X is radical 2 over 2. Y squared is radical 2 over 2 squared because x and y are the same. So, a little word of wisdom. On the side, I'm going to do radical 2 over 2 squared and radical 2 over 2 cubed as my little side work, and whatever those are, I'm going to plug them in for the appropriate term. What's radical 2 over 2 squared? Well, it's radical 2 squared over 2 squared. What is it? Just 1/2. It's not so bad. Now, isn't radical 2 over 2 cubed one more factor of radical 2 over 2? It's radical 2 over 2 times radical 2 over 2, 1/2, times radical 2 over 2. What's that?
Radical 2 over 4.
Radical 2 over 4. For those who are confused, you could do radical 2 times radical 2 times radical 2 over 2 times 2 times 2. Got a little chaotic out there, didn't it? We got to focus. Good enough for me. Do you need to pass or are you good?
Okay.
All right. What'd you guys get? Do you agree it's radical 2 over 4? Could you do that? Could you do it this way? I mean, this is 2 radical 2 over 8. Reduce 2 over 8, 1/4, right? Radical 2 over 4. Awesome. With that side work, we're ready to start evaluating. Are you ready to evaluate?
No.
Are you all ready for this? All right, it doesn't matter whether it's x cubed or y cubed. In this problem, x and y are the same. So what is radical 2 over 2 cubed? Radical 2 over 4. Ooh, that's going to cancel nicely. It's going to be beautiful. It's going to be beautiful, and then you're going to be really sad at the end. Okay? Minus 2x. X is radical 2 over 2. Ooh, that's going to cancel nicely. Times y squared, which is 1/2. Over 2 x squared is 1/2. Times y, which is radical 2 over 2, minus 2 radical 2 over 2. Get your canceling pencil ready. What if you had a canceling pencil? I just one ready to go. And it's like, this is my canceling pencil. Every time, I mean, it's exciting. It'd be like, it has a job. It has a purpose. It's ready to go. Ready? Negative radical 2. 2 times 1/2 is 1. Minus radical 2 over 2. All over. Radical 2 over 2. minus radical 2. What is it? -1? Not ready for it yet? Would you like to find common denominators? Let's do it. What's -2 radical 2 minus radical 2? What's -2 radical 2's minus a radical 2? -3 radical 2's over 2, right?
Yeah.
Yes?
Yes.
Fractions. Half of me gets them, half of me doesn't. The other half just isn't sure yet. Okay?
Oh, yeah.
Oh.
That's the joke. About fractions.
You don't understand.
Yeah.
I get it.
Yeah, just like math literacy affects 8 out of every 5 people. Man, bear, pig. Half man, half bear, half pig. Is that a South Park? Oh, it's been a while. All right. What's radical 2 over 2 minus 2 radical 2 over 2? If you have 1 radical 2 over 2 and you take away 2 radical 2's over 2, -1. Radical 2 over 2. Flip and multiply? Cole, I think we're missing something here. I think you're right. What am I missing here? Hold on, -2. -3 radical 2 over 2. Minus radical 2 over 2. Flip and multiply. So we're going to get a positive. We're going to multiply by 2. Flip and multiply 2 over radical 2. Those cancel. Get that canceling pencil ready. Those cancel. Did you get 3? I feel like it's not 3, though. Hold on. Let me check this. It is 3. What's 3? What does that mean? Slope of the tangent line at the point radical 2 over 2, comma radical 2 over 2. It's 3. That was fun. We needed that. You know, like in any good coach, when you're training, you overtrain, and then the game seems easy. This is like that moment. Man, those just gets your muscles going. Those math muscles. All right, what's my point of tangent C? Point of tangent. Oh, bad abbreviation. Point of tangent C. Radical 2 over 2. Radical 2 over 2. Tangent line. Y minus radical 2 over 2 equals 3 times x minus radical 2 over 2. This is that moment where I said earlier in the year you're not going to want to write it in anything other than point slope form. Just not necessary. All right, normal line. Y minus radical 2 over 2. What's the slope of the normal line? -1/3 x minus radical 2 over 2. So that was fun. Second derivative. It's time. Did you guys bring any math goggles? Things are going to get messy. Just like chemistry, it's good practice in the lab to have what? Black? Do you have goggles?
Oh, yeah.
Yeah.
You know why? Because you don't want to spill anything in your eyes, right? When things get messy, you want to protect your eyes, and things are about to get messy because people's minds are going to get blown. When people's minds get blown, you need some math goggles. Are you all ready for this?
Oh, yeah.
Let's get amped up. First derivative. First derivative. What's the derivative of x squared with respect to x? 2x. What's the derivative of y squared? 2y dy dx. Equals 0. Collect all the dy dx terms. 2y dy dx equals negative 2x. No factoring necessary here, just division. Dy dx is negative x over y. Do you agree? Negative x over y. It's second derivative time. The derivative of the left side is the second derivative of y with respect to x. What rule is appropriate for the derivative of negative x over y? The quotient rule. Low. D high. Minus. High. D low. All over. Low, low. What's the issue? What's up there that's causing us issues? I mean, we're fine with x's and y's. There's a dy dx. But it's okay. Don't fret. We know what dy dx is. It's negative x over y. Ooh, getting spicy. I appreciate that reaction. The plot thickens. Let's go ahead and clean it up as we go. Negative y plus x times. This one even gets a different color change. Negative x over, thank you, x over y. Some flair. Are you good? Let's go ahead and clean it up a bit. Negative y minus x squared over y squared. All right, that x up there is x over 1. I couldn't see something out there. I totally thought I was seeing the wrong thing. Okay. Ready to find some common denominators in the numerator? Wendy is. Let's go. If we want to make common denominators, this needs a y. This becomes a y squared. Agreed? Combine. Negative y squared minus x squared over y all over y squared. Get so excited. I'm getting ready. If there's a complex fraction, are you guys okay with just dropping that y down and making it y cubed? You could go you could keep flip switch. What'd you guys call it? Keep change flip. You could write this as y squared over 1 and then flip, I guess. And then that's y cubed. But from now on, it's going to save you some time if you just recognize fraction over a fraction, that denominator up top can drop down and multiply to the denominator in the bottom. All right? So we have negative y squared minus x squared over y cubed. And now we have it written as one nice fraction, isn't it? Isn't it? Ready for the final answer? Should we box it in? Put them on. Safe lab practices. Oh, Tony. You gonna do it, Tony? Yes. Yes. Let's go.
Wow.
Let's go.
Oh.
Who's got it? Gavin. You see it?
Yeah.
You guys see it? Hold on. Take off your goggles for a second. Maybe you didn't see it because of that. Take off your goggles. Okay. You see it? You ready? X squared plus y squared is 25.
You're lying. You're lying.
It was hiding all along. Wasn't it? X squared plus y squared is 25. Boom. Second derivative. Was that fun? So, did you recognize this thing? This is our good old friend. Who is this? Who'd we start off with? Yes. A circle centered at the origin with a radius of. And here's what's crazy about this. And this is, we could spend a whole class period just talking about the attributes of this. First of all, not a function. Fails the vertical line test. So at any x, there could possibly be two outputs of slope, correct? This slope or that slope. But we found the second derivative. We found out the rate at which the slopes were changing. What's that? Negative 25 over y cubed. That's the rate at which the slopes on this circle are changing. It's kind of crazy, isn't it? Just think about that. Just zone out the rest of the day. Don't worry about your other classes. Just think about that. Okay? This is the only one you come for anyway, right? Don't tell your other teachers I said that. All right, we're not going to do this one. We're going to run out of time, but I want to at least approach it. First term, power rule, right? Plus, second term, power chain, right? Power chain. And then just a power rule over there, okay? That's the biggest part, is recognizing the appropriate rules for these. All right, let's discuss our homework for tonight. I'll get over yourselves. Let's double check these. I might add to that. Oh. All right, 2. Good. All right, on number 2, the other side of the equal sign, it's 18xy. 18 times x times y. What rule would you use for 18 times x times y? Product, good. Now question, could you write the 18 out front and then parentheses do the product rule on x times y? Yeah. Could you treat the first term as 8x? Nope, 18x. And the second term is y and do the product rule on that? Yes, either one will work. Okay? You could treat the first term as 18x, second term as y, or constant multiple 18 and then product rule on x times y. All right, that's number 2. Number 3, beautiful. 6, beautiful. 9, beautiful. 12, ugly but beautiful. Like the weird cats. 15, 18. You know what? Just because of the complaining, we're going to add 21 to it. That's the way you assert your dominance. Take that. Take that, class. You can thank Rick later. Oh, look at that timing.